Hello everyone. Today we are going to see frequency modulation in MATLAB. Previously we've seen amplitude modulation, and we see that in amplitude modulation we were modulating the message signal with a carrier signal which has a fixed frequency. There's another way of modulating signal with varying the frequency of the carrier signal. This time we are not varying the amplitude. The average amplitude of the modulated signal remains same over the time. So we are not dealing with the low and high amplitudes of the signal, and in this manner, frequency modulation provides better discrimination against noise and interference. This better performance against noise, however, comes with a trade-off, as we will see in the frequency domain in this code. So let's start the code. As before, we are defining sampling frequency of system. Frequency of message signal in here, and frequency of the carrier signal. What's different than the amplitude modulation in here, that we use a term called delta F in here, which means the variation on the carrier signal. And another difference is, as you can see from this equation from Huygens book, we have to implement an integral operation in here, as you can see. So I added actually these lines for this integration operation, but you can use sum function of the MATLAB, which takes the summation of the vector elements instead of these lines. So let's see the time domain representations of the signal by plotting. Since our varying frequency value in here is not that high, we can't see the effect in this graph actually. To see the change in the frequency, you can always set delta F to a higher value. So let's try that too. Let's see. Let's change the delta F to 1000. Now you can see the frequency difference in this graph. We now see the huge difference on the modulated signal. When the message signal decrease, we have a signal which has a very low frequency, and much higher signal when the message signal increase. Let's return to our original value of delta F, and let's see the frequency spectrum actually. As you can see from here, in frequency modulation, we have a larger occupied bandwidth in the sides. This is the trade-off of having a better performance against the noise. We have to occupy a larger bandwidth. And another thing is that if you increase the frequency deviation and has the modulation index, you will see more sidebands in here. And in theory, actually, there will be an infinite number of sidebands in the frequency modulation because of the nature of the Fourier transformation. However, according to Carson's rule, 98% of signal power in frequency modulation is contained within a bandwidth equal to deviation frequency plus the modulation frequency doubled. So we just ignore the sidebands which have very low magnitudes. So let's see the demolition of the signal. It starts from here. Actually, there are two ways of demodulating signal in frequency domain. The first one is called frequency discriminator, which relies on slope detection followed by an envelope detector. The other one, called a phase lock loop, performs frequency demolition in a somewhat indirect manner. We will use the first one in here. First, we will differentiate the signal. You can see the differentiation in here. I added this line to equalize the um, length of the vector of differentiator result. And the same process with an envelope detector that used in amplitude modulation in here. This is the same lines, same codes that I used in the amplitude modulation. So we just using input for differentiation result instead of the actually modulated signal. So let's see the frequency domain representation of the demodulated signal. As you can see, let's click these points. We have only frequency parts on the message signal parts, and in frequency we can see that only lower part of signal remains in here. And let's see in the time domain. This is actually really looks like the message signal at first. And if you want to eliminate these ripples in here, you can always increase the order of the filter. So let's try that too, lastly. So I increase the order of the filter to 10. And this is more perfect, more smooth way of the representation of the demodulated signal in time domain. So that was all the things that I can say about frequency modulation. Thanks for watching, and if you want to access the codes, I always put the link in the description of the videos. Thanks again.